All right, good afternoon, everyone. If I can have your attention, we're going to start in just a minute, or maybe just a few seconds. Thank you very much for listening. All right, okay, let's get started. All right. Hello, everyone. Welcome. My name is Harriet Bredor. I'm the Exec Director here at the Keck Institute for Space Studies. It is such a pleasure to welcome so many friendly faces and new faces here today. We've got a fantastic lineup for our KISS showcase here this afternoon, and then that's going to be followed by our Caltech JPL networking mixer as well. So we're going to be spoiling you with some fantastic updates of some of our recent KISS studies that a number of people in the audience have been working very hard on in recent years. And then we're going to continue those conversations going forward as well. So really the idea of today is to introduce you a little bit more to the Keck Institute for Space Studies, share a little bit more about what we're doing, what our community is working on, and hopefully foster some of those conversations to help take those ideas to the next level, but also hopefully there's some new ideas that come out of the discussions that we'll be fostering here today as well. So I've got a little bit of a run through of what we can look forward to. So we have got a jam-packed showcase for you today. We were really blown away by the number of leads and participants who wanted to share updates from their recent studies. So a huge thank you to everyone who is going to be giving us an update today. We are really covering the breadth of space studies. So we define space studies here at KISS in the broadest possible sense. So we're going to be hearing about topics from across the solar system, astronomy and astrophysics, technology and earth science as well. So hopefully there is something for everyone to learn later on during this session. We're also going to have some time for Q&A as well. So we're going to be using Slido. So just to give you a heads up, there will be QR codes popping up on the screen. So if you have a burning question for any of our speakers, please do scan that when it comes up, and we'll be sure to field some of those questions as much as we have time for today. But also the whole purpose of the networking mixer after that is for us to get to know each other and continue those conversations as well. So if you have a burning question that doesn't quite get answered, please do make a mental note and go and see that person for a drink afterwards as well. So with that, I just wanted to give a quick introduction before I hand over to our fantastic study leads to hear more about the work of KISS. But before we do that, I want to give a little bit of an introduction. So maybe before we start, hands up if you have participated in a KISS study before. All right, that's a pretty impressive show of hands. And hands up if you're completely new to KISS. This is the first time you've interacted. All right, still a number of hands. All right, okay, so we've got a nice mix, which is fantastic. So just to give a little bit of background for those folks who are maybe unfamiliar, the Keck Institute for Space Studies was established at Caltech in 2008 with initial grant from the Keck Foundation, which is where we get our name. We are a think and do tank, and so we're really working to help shape the future of space exploration, science and technology through 3 core objectives, and hopefully you'll hear a little bit more about that from our study leads throughout the course of this showcase. We're looking to develop ideas and concepts that can revolutionize space science and engineering. We're also here to foster collaboration. That's really key. That's why we have the networking afterwards as well. We're looking to bring together our colleagues from Caltech and JPL, but also the wider space science and technology community, and also empower future leaders of the space community as well. So hands up, I saw we've got a couple of our KISS affiliates in the audience. Okay, don't be shy. Fantastic. So we also have the best and brightest of our Caltech grad students and postdocs that we support through our affiliates program as well. So we're really glad to have some of them with us today as well. Before we jump in, I just wanted to say a little bit more about what we've been up to in the last year at KISS. We have been busy, which has been fantastic, and I just wanted to share a couple of the highlights from our institute perspective, and then you'll hear a lot more from folks later on some of the specifics. Every year we support a number of different study programs that bring together experts from across different space science and technology communities through a series of workshops. In the last year we have supported 5 study programs, 8 workshops. We've had 3 final reports published. There are many more to come. I'm going to be looking at people in the audience for those who are mid-drafting. We also offer public short courses, so please do check out our website for those updates that we have available. We had a fantastic symposium, and we're going to be hearing from Adriana about that later on. Public lectures, co-hosted events, and also our fantastic affiliate program that I mentioned as well. And one of the things that we're looking to do more of is to celebrate and showcase the fantastic impact that comes out of those KISS studies that we support. So the idea is that the studies and the workshops that we convene are really just the start of those ideas and collaborations that we can take forward. You might see some friendly faces of people in the audience who are in these wonderful photos. It's been a really busy year for KISS, and I just want to say we wouldn't be where we are without the fantastic community of folks that get involved in our studies, engage with our programs, and take those ideas to the next level. So this really is a team effort and a community that we're looking to build here at KISS. So next up, I just wanted to share a little bit of a teaser of our updated video. So as I mentioned, KISS was founded in 2008. And in recent months, we've been working very hard with our fantastic team, AMT team here at Caltech, to work on an updated promo video that shares a little bit more about what KISS is, what we do, and what you can expect to learn more from our program. So I have got a little teaser for that I'm going to just play now.
The Keck Institute for Space Studies is Caltech's Think Do tank for space exploration. We look at advanced out there concepts for how to observe the Earth, how to gaze into the heavens beyond, and then what are the technologies that enable us to explore and create the data sets of the future. KISS's mission is to revolutionize space studies. We seek far out concepts that have breakthrough potential and seed the teams and investigators behind those concepts.
It's a really passionate group of experts that we're bringing together who really see a positive, expansive future.
I think what makes KISS unique is the level of ambition of the ideas that are being discussed.
It takes crazy ideas and it funnels them and channels them into something that is actionable and yet truly futuristic.
That kind of far out thinking lays the ground for audacious missions of the future and audacious technologies, and that's what KISS seeks to enable, is to make what is presently impossible possible.
All right, so that is just our teaser. Oh yeah, let's give it a... And this is a round of applause for our fantastic media team who worked incredibly hard. We have a longer version that is coming out very shortly as well, and I just want to say a huge thank you to everyone that we interviewed for that video. We could have made a 90-minute documentary, and we may still do that. So before we do that, however, let's go back to our slides. So this is a little bit of a shout out for those folks who raised their hands who have been involved in KISS studies in the past. If you were inspired or you remember something that's happened in a past KISS study that you were involved in, please do share it with us. We want to hear about those past impacts and updates so that we can learn more and celebrate and champion the activities that are coming out of our KISS studies. So this is just a reminder, we'll share this later on as well, but we do have an impact survey. We're always keen to learn more from you about what has happened with our KISS studies since they go off into the big wide world. But with that, I am going to stop talking because I want to hear from our fantastic group of speakers that we have here. So we're going to be doing this quick fire style. We're going to have 5 minutes max from each of our fantastic speakers. The way that we're going to do this is we're going to do it in 2 parts. So we're going to hear from 8 of our study leads, and then we're going to go into Q&A. There will be QR codes coming up in between each of the talks. So if you do have a burning question, you can go into slido.com or scan the QR code. All the instructions will be coming up on the screen. We're going to be hearing from a whole range of different talks and topics today. And without further ado, I would like to ask our first speaker, Kent Wallace, to come up to the stage. If any of the other study leads see their study up on the board, please be prepared to come up in order. We're going to be keeping to time. So really appreciate us flying through and really excited to learn about what everyone has been working on. So with that, I'm going to hand over to Kent.
Great. Thank you very much, Harriet. It's really great to be able to share how much I value the Keck Institute. It's really helped propel a lot of our work forward. So I'll be discussing metasurface optics for high contrast imaging. This is a workshop that we held last September. We brought together two groups, exoplanet scientists and nanofabrication technologists, and we mashed them together. The goal was to explore ways to combine these two fields of research. The group represented institutions from not only across the country, but from around the world. And as part of that work, we recommended 3 strategic areas of technology development. The first is metasurface chronographic mass. Let me take a step back and just say that, answer the question, what are metasurfaces? I think of them as like optical stubble, if you will. What I mean is these are very small dielectric nanopillars that are on a regular array, but they can be engineered and designed to modify the phase and amplitude and polarization of light at very fine spatial scales. And there's a huge benefit for being able to engineer surfaces like that. So as a result of all of this week-long workshop, we came up with 3 strategic areas of technology development. The first is chronographic mask, second is polarization aberration correction, and the third is dual-purpose focal plane mask, where you do wavefront sensing and high-contrast imaging using the same device. Lower right is a representation of how we use these devices in order to create the high-contrast condition to enable spectroscopy. And it's also the front page of our final report, which is coming soon. I just want to give a quick update on some of the technological highlights that we've accomplished. This is actually since our workshop in September. On the left is an example of what we've done with regards to the fabrication of these dual-purpose masks. So what you see is what looks to be like a blue mirror in reflection. That's because short wavelength light is being reflected from this mask. Long wavelength light is being transmitted. Long wavelength will be used for high contrast imaging. But at the very center of this substrate, we deposit first a hard-edge chronographic puck, and at the center of that, we place our metasurface device, and the data in the center shows us that the metasurface device is acting as expected. It's extending the dynamic range of the Zernike wavefront sensor, and this will allow us to do wavefront correction while we're doing science observation. And on the right, we show our progress on making these vortex masks using metasurfaces as well. So these masks use geometric phase, which makes them more broadband. So we're continuing to make steady progress in this area of research. Just a quick highlight on some of the proposals that have been submitted. There was an SAT that was submitted by Tobias, who's here today with us, for the workshop members. There is one submitted by Max Millar-Blanchard at UC Santa Barbara. He was also a member of the workshop and included 7 other workshop members. And then one submitted by Mikael, who is in Sweden. They're supporting some of the vortex development as well. And we've also had work that has been awarded as well. This is as it relates to the polarization aberration correction. So this is work that was submitted internally to JPL. It's already been funded, which is really great. It has this opportunity to make a significant impact on HWO. So we're really excited to already start to begin the technology development for that work. And we've had a few papers that have already been published. Again, this is since the workshop. So the group at UC Santa Barbara, in collaboration with Tobias and I and others, are working on the fabrication of these metasurface vortex masks. And Tobias and I have written a paper on how to do metrology of these devices, as well as how to extend their capabilities. And then finally, a paper, again, by Mikael, showing the work that's being planned in Europe for HWO. So all very recent work, all very exciting work related to this topic. Thank you.
Fantastic. All right. Round of applause for Kent. Thank you. All right, fantastic. So our next speaker is George Javosky. So as he is making his way up to the screen, if you have any questions for our first batch of panelists, just a reminder, we will have this Slido QR code coming up after each talk. And with that, George, I'm going to hand over to you. Thank you very much. Would you like the clicker?
No.
Great.
Well, good afternoon, everybody. I'll be talking about a workshop on data-driven approaches to search for techno-signatures of advanced civilizations, and if nothing else, just demonstrated that KISS is not afraid to boldly go where no workshop has gone before. And my colleagues were Joe Lazio, Andrew Howard, and Kurt Cutler. And at the time, Tom Prince told me that when our proposal was reviewed, half the committee thought it was too crazy even for KISS. And the other half thought it wasn't crazy enough. So he averaged the two, and here we are. As you know, exoplanetology is a booming field, and among other things, it includes searches for biosignatures, life on other planets, that life could evolve intelligence and then technology, and maybe in some cases that technology would be detectable from planet Earth. Traditionally, this was done by SETI, which is based on several assumptions. First, that advanced civilization will want to communicate with us. Then they will do this using Earth-based mid-20th century technology in a way that we can understand. I think there is a much better, less biased approach to this that's afforded by vast new multi-wavelength, multi-epoch data sets from sky surveys, and new tools to explore it from machine learning and AI to look for sources in the sky that do not look like anything else in those surveys. There are a lot of possible anthropocentric biases, and we are working really hard to avoid them. So we decided we can only trust mathematics, physics, chemistry, and information theory as universal, and everything else is up for discussion. We also noted that organisms and civilizations and everything in between consume energy and then radiate it away as waste heat. And that can give us some hints what to look for. A good example of that are Dyson spheres. So our first approach was to get one or more sky surveys, combine them together with properties of all detected sources. They form huge feature space, hundreds of dimensions at least, and then unleash different machine learning algorithms for unsupervised clustering, anomaly detection, and so on. And there are many interesting methodological issues there. And the upshot is they can find in some well-described, statistically significant way objects that do not belong to any one of the known classes, stars or galaxies or whatever. And there are lots of those in all sky surveys, and almost all of them are just artifacts for some reason. But some are not, and so surveys so far have found new rare types of supernovae or quasars and stuff like that. Someday, maybe technosignatures. So the upshot is that search for technosignatures is really collateral benefit of an ongoing work with sky surveys, sort of comes at no cost. The other approach is to look for artifacts in solar system, and they come in two flavors. Things on surfaces of solar system bodies which do not have atmosphere, so they can be there for millions of years. And we have test data set in form of Apollo landing sites on the moon. And several groups have actually tried to devise algorithm that will show this is not a natural formation, this is something different from everything else in those images. Alternatively, they can be free flyers, think defunct probe that orbits a planet or sun, both, and does so on some unusual orbit. Lots of asteroids get captured for that. But what's an unusual orbit? So turns out that databases of orbital parameters of asteroids are a royal mess, and too early to do this project properly. But there are interesting things, like this asteroid here that orbits the Earth in this weird orbit and follows the Earth as it goes around the sun. So that hasn't been done yet, and I will stop here and just leave you with this.
Thank you, George. Wonderful. Thank you. All right. Okay. Next up, we have, I think, Greg is going to be joining us. Yes. Thank you, Greg. All right. Just a reminder, we have the QR code. If you have questions for any of our speakers, please do scan that. And with that, I will hand over to you, Greg.
Okay. Thank you very much, Harriet. Okay. So I'm going to talk about our workshop, which is called Blazing Paths to Observing Stellar and Exoplanet Particle Environments. My co-leads were Joe Lazio, who you'll see on many of these workshops, Evgeny Skolnick, and Park Lloyd, who did a lot of the heavy lifting, getting us all organized. And as you've seen before, for other workshops, the outcome, of course, is to get a report that really maps a path forward, and we're pretty darn close to being able to release ours in the near future. And this was an amazing conference and an amazing team. I have to say this is probably the most fun I've ever had at a workshop. And I think it might have been your first one, Harriet, actually, at KISS, right? So that was awesome. Okay, so some background context. The activity of a star can significantly impact the environment of a planet, and over longer timescales impact the evolution of an atmosphere and even habitability. There are more than one type of space weather to keep in mind here. The radiation associated with magnetic reconnection-driven flares leads to higher increases in X-ray and UV flux that can heat the atmosphere, leading to extended thermospheres and atmospheric loss. You can have particle flux, CMEs, coronal mass ejections, solar energetic particle events. They can erode atmospheres via different processes like ion pickup. When extending to other stars, there's a lot of data on flares and a lot of modeling on the impact, and there's a real dearth of any information on the particle flux experienced by planets orbiting stars and their impact. Impact could be negative, impact could be positive in some contexts. Maybe the high energy particles can play a role in biogenesis, for example. These are all open questions, and I think it's a very timely question because, of course, we're getting the first direct characterization of the atmospheres of small and rocky planets thanks to James Webb. These are small planets orbiting a very particular flavor of stars. In some cases, we're seeing some bare rocks, although that's still hotly debated. Key point is, with that atmospheric characterization, we're getting to the point where information about the particle environment and models that understand the impact elucidate on the impact of those particles in atmospheres is very timely. So this kind of movie, if it plays, summarizes this picture, I think, pretty well. There we go. The question we're asking really is just how important are particles in the forms of CMEs as well as SEP events in defining the atmospheric properties of small rocky planets orbiting stars that are very different to our own sun. And maybe also a related question is how important are the magnetic fields of those planets in protecting the atmospheres from those stars. We went through a very laborious process. I promise you I'm not going to talk you through all this in detail, but the properties of the planets and the stars and the types of ways that we can probe the particle flux and the modeling that we need to interpret that data were all on the table for our conversation. We talked through every mechanism for direct characterization of winds, CMEs, both by observing them directly as well as characterizing them through impact on the planet. We had lots of crazy ideas, some that are less crazy, some that are very crazy, to try to do this in the near future and far future. One very obvious way to do this is to look for CMEs by the process of coronal dimming, i.e. the subsequent reduction in UV and X-ray flux you see when you've got a big bubble of cooler plasma sitting in front of the star. This is absolutely one of the ones where I never thought we would end up, and that is the idea of looking for CMEs and stellar wind through direct imaging in the same way we do for the sun, i.e. via Thomson scattering and chronography. I did not think we'd end up here, but it turns out to be just about feasible. And as well as some techniques that have been long proposed but not realized, and that includes sensitive interferometry from space to look for signatures like type 2 and type 3 bursts as ways to directly track particle flux, particles leaving from the star, and as well as tracking the auroral emissions of the planets orbiting those stars as a way to monitor that flux indirectly. The report has a series of conclusions and recommendations, as well as many of these paths forwards that are captured. And I'll stop there. Thank you.
All right, thank you, Greg. And final report coming to a KISS website near you soon, right? Very soon. Very soon. Fantastic. All right, perfect. Well, Chaz, you're ready to go, in which case I will hand over to you. Thank you very much.
Great. I'd like to talk to you about a technique that's always 20 years in the future, which is exploring exoplanets with interferometry. The great promise of interferometry is you can break the resolution of a telescope, which is proportional to the baseline, the separation between your apertures, and the collecting area of the telescope, which is proportional to its diameter. So if you want to be able to get down to sort of the milliarc seconds that you'd like to explore and separate the light of a planet from the light of the star, you want to have telescope separated by maybe even tens or hundreds of meters, and that's now being done on a couple of ground-based telescopes right up here in Mount Wilson, the Chara array, also down in Chile with the VLT, Very Large Telescope Interferometer. And you combine the light beams from these telescopes directly, creating interference patterns, you analyze those, and the sort of results we're getting now from Chara, from the VLT, are the actual sizes and diameters, and sometimes the change the elongation of some of the host stars that are hosts to planets. We're also getting spectra and orbits of individual planets in the HR 799 system, and looking for brown dwarfs, which might be binary systems. And there's this long-term promise of actually measuring the biosignatures of habitable zone Earths from space that I'll touch on in a moment. So we had a workshop with 30 participants from 16 different organizations, 7 different countries. The major players are from the US, France, Netherlands, Japan, and we discussed various technologies to putting telescopes either on separated spacecraft or on the moon. We'll hear a bit more about a lunar interferometer from another study in a couple of minutes. And then we discussed various precursor and technology demonstration projects. There's a Japanese interferometry small sat called Sirius, which has been selected for flight in 2030, and it was one of the major discussion points of our workshop. And there's another Japanese mission, Sylvia, that's in a down select competition for sometime 2032, and we're looking to build up a Japanese collaboration between the US and Japan on that. John Monnier, one of the participants, has a small sat also that's already been awarded to do this as well with separated spacecraft, and again, a possible lunar interferometer. And as I mentioned, a long-term goal is to use something like what we see here in the in this image here of 4 separated spacecraft, each holding like a 1-meter telescope, separated by a few 50 to 100 meters, sending light to a central collector. And with that, you could separate the light of the planet from the light of the star, and operating in the mid-infrared, look for species like CO2 and ozone, which would complement what the Habitable Worlds Observatory hopes to do in the visible range, things like the oxygen A-band here, and together by combining the visible light and mid-infrared, you can get things like the temperature of the planet, the radius of the planet, its albedo, and really start to fully characterize the planet in a way that one wavelength regime without the other really cannot do. So we had a very exciting meeting. We explored a whole range of interferometry techniques, both astrometry, spectroscopy, and direct imaging. We developed collaborations between Caltech and JPL scientists with outside astronomers from the US and Japan, and in Europe, the LIFE mission, and there was a follow-up study for lunar interferometry. And we really brought in a number of early career scientists, and since interferometry is often called the technique of the future, it was important to be able to hand on the heritage of missions such as the Space Interferometer mission and TPFI and Darwin to bring a new set of people to be engaged with that to hopefully move forward and find new opportunities.
Fantastic. Thank you, Chaz. All right. Okay, we're going to stick on the topic of interferometry, but we're going to move over to the moon, and we're going to hear from Stuart. So as Stuart is making his way down here, just a reminder, if you have any questions for any of our speakers, it's the same QR code for the first batch of speakers. So if you have any questions for anyone you've heard so far, please do scan that, and we will have a Q&A session coming up. And with that, I will hand over to Stuart. Thank you.
Thank you. Everybody, thank you. Where's my slide? Next slide, I guess. Okay, great. So we, the picture that you're seeing on the your right there, several years ago would have seemed very, very far off in the future. Chaz described it as the science of the science of the future, but in fact there are some developments that are happening now that make it possible in the next handful of years. What you're looking at in that picture is an artist's conception of a lunar interferometer. It's a long baseline interferometer, and as Chaz was saying, a long baseline interferometer is a distributed set of telescopes that you can use to perform very high resolution angular imaging. And as he also mentioned, we're standing in the shadow of the Chera array up on Mount Wilson. That's a 300-meter baseline. And in fact, Mount Wilson is where Michelson did the very first long baseline interferometer experiment about 100 years ago. So the technology is well in hand for doing that, but not on the moon. The other development is that NASA has this program called Artemis, and along with that, the commercial lunar payload system, CLPS, which is delivering spacecraft to the moon on a pretty regular basis. And there's an image from last month of a mission that landed on the moon, and it delivered a number of experiments doing X-rays and navigation and digging into the lunar surface and so forth, stereo imaging. So, and part of the program is to deliver mobility to the moon too, in the form of robotics. So with all of this coming together, it was a good time to hold a workshop and bring together people from the lunar industry, academia, engineering, astronomy, the scientists, interferometrists, and that formed the basis of this workshop. There were key things to consider, all of these developments, but also the possibilities of proposals through NASA at different scales. Let me just show you where we kind of ended up, because we studied 3 different scales of missions. The first one would be the simplest, and this had actually been proposed, something similar to this prior to the workshop, and it's called Moonlight, and it's a set of 2 telescopes, a very simple long baseline interferometer. They could be delivered by rovers, they could be connected by single mode fiber optics, and they would be able to measure the diameters of stars. That would be kind of the main science that would do. But building upon that, the next level that we could do, again with 2 telescopes, would be a very high precision instrument that could do astrometry down to about 1/10 of a microarc second, again with a 100-meter baseline. The purpose of this would be to measure the wobble of stars and identify stars that host planets, such Earth-like planets, and these would be targets that could be used for the habitable, or that would be observed by the Habitable Worlds Observatory. It's very important for that major observatory, which was #1 in the last decadal. It's very important for that to be able to identify targets ahead of time, so it's able to efficiently go and observe and characterize those planets. So that's what this mission concept would do. And then finally, a much more ambitious project would have a much larger baseline and a number of telescopes, maybe 1 meter in scale. The ones that you see here are very small, a few centimeter scale here, maybe 30 centimeter scale in the middle, and up to a meter class on the right. And that would be able to image the accretion disks around black holes and do a lot of high energy astrophysics, and would work in the ultraviolet. So this is kind of the scale of missions that were studied. We don't have much to say. This was just held in November, so it's still very recent. So we can't say that there's been a lot of development since then, but there is a lot of activity going on in this area, and I think our report's going to go a long ways toward helping to consolidate these things. Thank you.
Fantastic. Thank you, Stuart. All right. And again, final report coming to a KISS website near you very soon. So stay tuned. All right. Fantastic. Well, John's already here, ready to go. Over to you, John. Thank you.
Much, Harriet. So I'm the representative of a very recently completed KISS workshop on sample return from across the solar system. This was organized, I'd say it's the brainchild of Matthew Chakran up at JPL, with me participating, as did Hope Ishii from University of Hawaii. So this was a really fascinating workshop because of the breadth of topics that are involved in sample return science. The concept is you go somewhere, so propulsion, navigation, mission design are all key. You get somewhere and collect a sample, so robotics, navigation, autonomous operations, all kinds of things like this are important. You get home, and then you study in the laboratory. And so it follows the full arc of technologies, all in the service of some very specific motivating science questions. It's also a very international problem, and is becoming more so as JAXA, ESA, the Chinese Space Agency, India, Russia's back in the game. So there's many different players who are engaged in solar system exploration through sample return science. We had many of them represented among our 30 participants. The sorts of questions that we worked on span the full scope of things that I just described. But I think it's more useful to back up and think about the motivating science. These are very high cost, high stakes sorts of missions. They're things that are, you get very few bites at this apple. And so the motivating science has to be very compelling. One that comes up repeatedly in sample return science is searching for evidence of life on other planets. This is one of these things that's sort of like listening for TV shows from other planets that we heard about a few minutes ago, except you're looking for microbial remains, chemical evidence of extant life on other planets, and so forth. Extremely high stakes implications for our understanding of the history and distribution of life in the universe. But who's to say you ever find it, okay? And so it's one of these really edge case things that you try to engineer towards. The locations that we talked about the most for this are Mars, obviously, but then also the large number of outer solar system bodies that have subsurface oceans and icy crusts that we imagine might be habitable. Understanding the pathway of what's called prebiotic chemistry, that is, the chemistry of the universe is to first order organic, and somehow, at least once, that chemistry has organized itself into life. What is the pathway that organic chemistry that we find everywhere follows such that it can finally emerge as life in at least one place? So we need to see this in many different environments in the solar system, and the icy outer solar system bodies, or Ceres, is actually an interesting target because it's nearby, is organic rich, and has water on its surface, or has had water near its surface. The history information of solar system bodies, this is done through documenting the chemistry of objects that have known dynamical histories. We know a lot about this from meteorites, but they're all from the asteroid belt. We know a lot about the Earth, but the solar system more broadly, inside of the Earth's orbit, outside of the orbit of Mars and the asteroid belt, we know almost nothing. So going there and getting pieces, documenting their chemistry is key. Ices, the surfaces of virtually every body that you might want to visit in the solar system, have ice on them. The moon has ice on it. And so this is a material that we know a little bit about in the abstract, and in laboratory models, we know almost nothing about the study of these materials in their environment. And then finally, resources. So there is an economic geology of the solar system that has been speculated about for many years and is now turning into a reality. So laboratory study of these materials, getting them back home, is essential for a variety of reasons. There are properties you can't see remotely. Earth labs vastly outperform anything that you can do in situ, and more importantly, you can iterate, you can innovate, you can adapt your technology to the sample when you get things back in the lab, and you can relate to geology and so forth. So I will leave you with this map of different sorts of missions that have been taking place, that is sample return missions, over time. This is a subject that kicked off with a bang in the 70s through Mars or lunar sample return, had a brief revival looking at the sun and comets in the around 2000, and has just exploded around us. So there are many players, many targets. It's something that has become extremely active just in the last few years, and we project will be extremely active for the next decade or two. Okay, thanks.
All right, fantastic. Thank you, John. All right, fantastic. Okay, we've had a couple of questions come up on the Slido. Please do keep those coming in if you have any more. And with that, I'm going to hand over to our next speaker, penultimate in this session. So Chris, it's all yours. Thank you.
Thank you, Harriet. So I had a couple goals with this slide. The first was to put more pictures of Uranus than I've ever put on a slide before. The second is just to get across that despite the fact that we have the best remote information about Uranus than ever, thanks to, say, the James Webb Space Telescope, which gave us images like these bottom two images. The one on the bottom right shows a rich view of the Uranian system with its rings and moons and nearby stars and galaxies in the background. Nonetheless, there is a ton that we don't understand about Uranus, and we're hoping to learn more about it by exploring it directly with spacecraft. And so it is a major goal put forth in the last Planetary Science Decadal Survey to do a flagship class mission to explore the Uranian system. And this is kind of the main motivation for our workshop that we did in September 2023. This was a workshop that was led by Mark Hofstadter at JPL, Ravit Khaled at University of Zurich, and David Stevenson here at Caltech. And the report is out, I'm happy to say. It was a delight to see an actual paper copy when I came here to register, which I hadn't seen before, so that was a treat. So the intent of this workshop was really to build on the science goals that were laid out in this Planetary Decadal Survey. It was to define knowledge gaps that we need to work on here on Earth before we can refine science and instrument requirements for a Uranus orbiter and probe mission, and to try to get ready for those measurements and their analysis. So I recommend that you check out this report. It recommends measurements along many lines: atmospheric noble gas abundances, isotopic ratios, the gravity field of the planet, the magnetic field of the planet, its atmospheric energy balance and thermal structure in the atmosphere, waves in the rings to try to do seismology of the planet. So this ended up being a really interdisciplinary group of interior scientists and atmospheric scientists, material and physical chemistry experts, to work on the major questions of Uranus's interior. There are a number of knowledge gaps identified in the study, and there's already been a lot of work on these topics. Here's kind of a list of the papers that have come out so far that have acknowledged our 2023 study. There are papers on the dynamics of the Uranus and its moon system, possibly suggesting strong tidal dissipation in the planet. There's a couple studies from JPL, one on sort of architecture of the orbital tour for Uranus orbiter and how we can use that orbiter trajectory to do gravity science of the planet to learn about its interior mass distribution. Studies into how we can use probe measurements of atmospheric composition to hopefully learn about the bulk composition of the planet, which otherwise is pretty mysterious. Also, how we can try to use orbiter observations to do seismology of the planet, that is, understand its interior from the way that the planet oscillates. And also, new studies, this last one by J.J. Dong is a cool novel synthesis of kind of heterogeneous data sets for phase diagrams from iron and silicates that is really critical to building the next generation of interior models to understand observations from this kind of spacecraft. So this workshop had 29 participants from 13 institutions over 6 countries, and this is a picture not of the full group, but of just one of our focus groups. Those of you in the audience who've done a study know what this focus group atmosphere is like, and it's been kind of incredible. I've never had a meeting quite like that. And I definitely agree with Mark when he says that this kind of bringing together of people from such diverse groups to do this kind of intense, focused, very rewarding collaboration is something that I haven't experienced outside of KISS. So I'm very grateful for that. And I think we can move on. Thank you.
Super. Thank you so much, Chris. Appreciate it. All right, fantastic. So we have got our final presentation of this first block. And with that, I would like to invite Scott up to the stage. Thank you. And while Scott is getting up here, just a reminder, we have the Slido. If anyone has any questions, we'll be coming to those right after Scott. So with that, over to you. Thank you.
Thank you, everybody. So in terms of this study, this was done at the mid-2023 in terms of our first study. And there were two goals that we decided to proceed with. One was the understanding of what are the metrics in terms of biology, where if you were to make the measurement of that actual cell or that biomass, what would that actual measurement be? And the second goal was to understand how you'd make those measurements. So within our actual matrix itself, we would see here in terms of our matrix, each of those colored dots with regard to extent as well as extinct life, there's a series of measurements that can be made to understand what part of the cell or the actual biomass that those measurements are actually coming from. And so when it comes down to yield, if you have a full-on living system, the yield of what you're looking at in terms of biology is a lot higher than if the cells were dead. So this morph matrix that we actually came up with involves 5 large-scale categories that all biology can go forward with. And so the idea of it being a full-on system that, if it is living, you can make these measurements over and over again. And so the point was, where on Mars would we actually be able to make these measurements such that there's no surface contamination as well as desiccation in terms of everything that's actually exposed on the surface? So part of our first two goals, again, the measurements of full-on biology and the actual metrics of how you make those measurements were the first two goals in our first workshop. The second two goals involved how would you actually put that into a mission. So our final end goal here was a subsurface Mars mission that you'd be able to actually preserve the sedimentology as you go down into the subsurface, creating that environment where you're getting into the actual geologic history, but also anything that is preserved in the rock record as you go deeper. And our main goal is to get at least 10 meters into the Martian subsurface. And so when you have areas where there was groundwater recharge, you have hydrated minerals that could provide fluids that are still intact in the subsurface. And so fluid inclusions within salt minerals allow fluids to be actually preserved over geologic time fairly well. And so areas where you have salt minerals, in terms of what CRISM has seen all across Mars, these are sites where the water that formed these minerals likely went through groundwater downwelling to provide a path of where the water once was. So us allowing subsurface access for this paleoclimate record would get greater as we go deeper in this case. So when it came down to the actual, our main design of experiments in this case, we are leaving the habitability realm behind here. And so this is looking at what the actual microbiology-driven experiments would be to determine if there was life present or if there's actual life present right now on Mars. And the idea of it being within hydrated minerals provides a fairly limitless nutrient source in terms of a certain halophiles. So if you follow this actual matrix along, if you were in a system where the yield ended up being a certain amount, you'd be able to get an idea of relative age as you go deeper into the subsurface. So when it came down to that, our goals 3 and 4 were actually about the technologies needed. So we had the science done in the first year, completely independent of what the technologies that were used for the second year, for the second workshop in this case. And so that allowed us to have a full-on free science matrix independent of what missions and what technologies actually existed right now or still don't exist. And so this led, in terms of our goals 3 and 4, to what new technologies are needed in terms of geobiology and astrobiology. So we put this in for the NASA DARES proposals, and this is the response to the new decadal survey. And this is our first post-KISS effort in terms of getting this onto a mission platform in this case. So we had 2 workshops, like I mentioned, in 2023 and 2024. Our final report came out late last year, and so you can find it online. And since then, we've actually published a significant amount in these journals over here. And the timing of this actually went out pretty well because later this year is the 50th anniversary of the Viking mission. And so we're leading a special issue paper that would allow for what the next steps would be using our mission development as our next kind of Viking phase 2, if you will. And so in terms of where we're at, this is obviously the first year team, this is the second year team. And so as new NASA opportunities come up, we're looking to put in either technology development for what we're looking at, as well as fundamental research. So I'll leave this up here. In terms of publications, like I mentioned, we have these journals that are listed here. The Search for Life Science Analysis Group concluded late last year, and so we were able to actually provide to that. And I'll leave the rest up here in terms of KISS members as well as where they came from. Thank you.
All right, fantastic. Thank you, Scott. And I just want to say another round of applause for all of our first batch of speakers who all kept to time as well, which is an amazing achievement. All right, and with that, we are going to fly on to part 2. So we have got, now I know why, Joe, you are catching my eye. Yes. Now we've got a fantastic set of updates here as well. We're going to shift gears a little bit. We're going to move to some different areas of space studies. And to kick that off, we're going to hear from Joe, who actually I know as a fact, Joe wins the record for the participating in the most number of KISS workshops. I'll let you, we'll give Joe a round of applause.
Repeat offender, huh?
Yeah, so you get to guess what that number is, and whoever gets it right and tells me gets an extra free drink later on at the networking mixer. And with that, we'll hand over to Joe. Thank you.
Thanks, Harriet. So it's my pleasure to talk about this next generation ground-based planetary radar. We held 2 studies. If the dates don't register or if you've suppressed all those memories, here's our group photo. And a huge shout out to the KISS crew who pulled off, even in the depths of pandemic, the ability to do this successful workshop. The other thing that happened that may have been unique is this is what the world's planetary radar infrastructure looked like when we started the first workshop. This is what it looked like at the end. Arecibo collapsed between the two, and that actually led to a very interesting dynamic. In the first workshop, it was very much about here's what we have. And the second, it was about here's what we need. So we came up with 3, we started with the science. We started with science and we came up with 3 compelling science drivers for next generation planetary radar. The first is near-Earth asteroids. There's a science aspect to this, studying asteroids, primitive remnants of the solar system. But there's also an applied science aspect, namely tracking and characterizing asteroids is a key element of planetary defense. The extrasolar planet next door, Venus, or Earth's evil twin. So there are science questions such as, does it support volcanism today? What is the spin rate? How does that constrain the interior properties? And if you can penetrate the cloud layer and get to the surface, which radar observations can do, you can actually start to address some of those questions. Crucially, in the past 30 years, humanity, not just NASA, all of humanity has sent 3 spacecraft to Venus. And in that same interval, there have been a steady cadence of tens of radar observations to monitor its spin rate and monitor surface features through the radar observations. And then finally, looking toward the outer solar system, which of course of great interest from an ocean world perspective, some of the most compelling early observations that the outer moons, the outer solar system moons had ice on them, resulted from early radar observations. I'm highlighting Titan here because in part with radar you can penetrate the cloud depth. But we also now know that Titan has lakes in its northern hemisphere. And with a steady cadence of future radar observations, sufficiently good radar observations, you could actually track how those lakes change on a seasonal basis. And again, just to put that in perspective, Cassini, the interval between Cassini and Dragonfly is going to be something like half a Saturn orbit. Whereas if we had a radar, we could be able to be monitoring this on, say, an Earth year timescale. So that was the science case. And the other interesting thing that came out of the workshop is the technologies have matured. There's a new way of doing this. So rather than those big dishes that I showed you at the beginning, go to an array of smaller antennas, and you can combine them using interferometry, actually, which we've heard about a lot. And it's in fact a new way of doing it, but all of the technologies that we need are starting to mature and come together, and it's really turning into, it is feasible. Now, what has transpired since the workshop? Well, there was a planetary science and astrobiology decadal survey. We submitted a white paper to it, or there are actually several white papers, and language in the decadal survey is interestingly similar to what was in at least some of our white papers. The decadal survey recommended a study that be led by NASA and NSF. That study has actually now been conducted. It was led by the Aerospace Corporation, but multiple team members from our KISS study were interviewed multiple times by the aerospace leads to develop this matrix that they put together. I won't walk you through it, but it's essentially looking at what are the use cases and how would you actually execute those use cases in terms of an actual radar system. And I think the thing is, from a KISS perspective, the top of this matrix is kind of here's what we have today, and ambition goes downward and starts to match what we were discussing in the KISS workshop. So that was the KISS workshop. The only other thing, I'm going to leave you with a teaser of something very, very hot. It was not something that was discussed much at the workshop, but last month, you may have heard about the Lunar Trailblazer spacecraft and the mission. The Goldstone system, actually, between Goldstone and the Green Bank telescope, there were a series of radar tracks on the spacecraft to monitor its trajectory as it went out to the moon and then flew past it. And the radar systems provided some of the key navigation data, or some of the key data that the navigation team was able to use to confirm the trajectory of the spacecraft. And also, all of these four plots are showing the radar returns from the spacecraft. All of those fluctuations are real. All those dips and bumps are real, and they're being used or have been used to actually constrain the spin state of the spacecraft, and were an aspect of can it be recovered. So I'll leave you with that.
Super. Thank you, Joe. All right. Okay. We are going to move on. And just so a reminder, we now have a new Slido for the new set of questions. So if you have questions for Joe or anyone else who's coming up in this second half, please do scan this QR code. And with that, I'm going to hand over to Benji. All right. Over to you. Thank you.
Thank you. Like most studies here, geology are interested in ours too. So thanks for having us, and Joe, thanks for coming. We're here to talk about rapid response. So it's pretty self-explanatory. We want to go faster. How do we take a mission instead of doing it over the course of 5 years or 10 years? How do we see something in 6 months or 1 year or 2 years and actually do something about it? Why do we want to do that? Because every once in a while, by every couple of years, we go and something awesome comes by and we say, shoot, I wish we could have gone to see that. I wish we could have gone to send a spacecraft to go and explore something brilliant. So here are a couple really interesting objects that have flown through our solar system in the recent past, and it would have been really, really, really cool to get a dedicated spacecraft to understand the nature of these objects and help us understand both our solar system by studying long-period comets, and also perhaps other solar systems by studying objects that came from beyond our solar system. So here I feature a long-period comet and then 2 interstellar objects. We also want to do it because we don't want to miss an opportunity to go and serve planetary defense. So if there were to be an object that we need to go and do something about rapidly, we've had an example in our recent past with YR4 that was, I think it was the highest likelihood of impact of any other object. We want to have this capability to go and either perform reconnaissance or potentially mitigation of a planetary defense scenario. Also, Apophis is coming in 2029. In case you haven't heard or nobody has told you, it's a really exciting mission and we should send something to it. And to do that, well, the clock is ticking. We need a rapid response mission to be able to go and study this really interesting object. And through that, we should be able to understand how to prevent future objects like this from posing a threat to our Earth. So thank you very much for having me. Since our study, we have conducted, I think I have a chart on it. So we've conducted a number of different advocacy groups. We've presented a bunch of papers all around the world. Jim in the back, who is a co-lead on this study, was just last week in Tokyo discussing how rapid response can be enabling for future missions at the Apophis workshop. It was a really great study from participation from all over the world, so 3 different countries, 12 organizations. It was about a third, Alex said it was a third JPL, a third industry, and a third academia. So it was a very nice distribution of different people coming together to understand how to work this very important problem. How do we respond quickly to objects that we discover? So thank you very much. I appreciate your being here and happy to answer any questions.
Fantastic. Thank you, Benji. A wonderful, nice advertisement for our Slido. So if you have questions for Benji, please do scan the code. And that was a perfect segue, I think, into our next update to learn a little bit more about Apophis specifically and what our symposium last year was getting up to. So Adriana, over to you. Thank you.
Thanks, Harriet. Today I will be talking about a Caltech mission that is under development to go to Apophis. So as you just heard, Apophis is coming in 2029. I wonder if I can make this video play. And it will be actually passing by Earth within geostationary orbit and in 1/10 of the distance to the moon. So it's coming pretty close. And Caltech is working on a mission to rendezvous with Apophis, study its surface properties, observe how it might change due to Earth's tidal forces, and take bistatic radar measurements to look inside and characterize its internal structure. And this mission was actually under development previously at JPL, but now it's being led by Caltech, and we're pursuing it as a privately funded mission. So I'll have more updates about the funding situation later on. What else did I want to say? That's it for that slide. So we had our symposium here at Caltech last summer. We had 27 participants from 10 different organizations. It was mostly universities, a few NASA centers, JPL and Caltech. And what we wanted to get out of the symposium was really to review what we can learn from specific measurements at Apophis and how this will advance planetary science and planetary defense. And we wanted the symposium participants to provide guidance to the mission planning team to ensure the best science return. And then we also wanted to define how the open data would be utilized to progress planetary science and planetary defense. And then I'll go into an update about what we've been working on since the symposium. So the main 4 things were we've refined our science case for the mission, we discussed community impact and public outreach, and we definitely advanced early career engagement, and we're working on some exciting research projects. So we are currently in phase A. We actually have our first design review next week, next Friday, and we are very close to securing a deal for private funding for this mission. It's not finalized yet, but we're getting really close. And the outcomes from the symposium really helped us to sharpen the team objectives in this phase and strengthen our fundraising efforts. We also discussed public outreach and public communications for planetary defense. And here it's kind of hard, it's kind of small, but a notional app, actually, James Keen came up with a cool drawing and of like an Apophis tracker app that the public could use to track Apophis as it flies by and learn about it, which I hope we can implement. What else? And now, so we're working on a few different journal papers. So one of them is more of a review paper. We're discussing Apophis science, knowns and unknowns, and how the Caltech mission will advance planetary science and planetary defense, and learn more about Apophis. And we're also working on more of a modeling and simulation paper, so using discrete element method to simulate Apophis's reaction to the Earth's tidal forces as it flies by. So here's just an image of an example of a rubble pile model of Apophis. If I didn't mention it earlier, we think it's a rubble pile, so it's not just one large piece of rock, it's a bunch of granular materials held together by its own gravity. And we want to see how it's going to react when it flies by, and we're looking forward to it. Thank you.
Great. Thank you. Fantastic. Thank you, Adriana. All right, super. So I'll just keep this QR code up there for just a couple of seconds. Fantastic. All right. So we've heard from a number of different KISS studies already today. The other thing that we also do support at KISS is funding and facilitating the funding of follow-on technology development that is associated with some of our activities and space studies as well. So with that, very happy to introduce Austin to tell us a little bit more about his work. Thank you.
Yeah, thanks, Harriet, and thank you all for attending today. Yeah, so we heard at the beginning that KISS aims to be a think and do tank. So today I want to tell you a little bit about the do part, where we're trying to make these low noise transistors even better. Low noise transistors, based on the high electron mobility transistors, are used really everywhere in space science. So at the left is this very famous image of the black hole, the first ever taken. This was taken in about 250 gigahertz or so. And after that radiation from the black hole was mixed down by a superconducting mixer, it hit a HEMT, as we call them, high electron mobility transistor. In addition, for planetary or Earth science specifically, microwave observations are used for temperature measurements of the atmospheric column, moisture content, and all sorts of things. And even in just what we've heard so far in this symposium, it was already mentioned that microwave radiometry can be used for Uranus water content, for radio interferometry, and untold other applications. So this is what a transistor looks like from the side. This is just one part of the whole structure of it, but it's the most important part, where the gate is behind that red trapezoid. And the way the device works is you apply a voltage to this terminal, and that kind of wiggles the electron density that's inside the channel. So if you want to make a better transistor, a lower noise one, you have to figure out where the noise is coming from. Over the decades, there's two noise sources that were found. One was thought to be from the gate itself, just because of thermal noise. But then there's this other noise source which seemed to be having a temperature much greater than the ambient temperature, but the mechanism really wasn't clear. And so it was given the name hot electron noise. For many decades, we could kind of ignore the fact that we didn't really understand the origin of this noise source and just make the transistors better by shrinking everything. So if you shrink the gate length in the horizontal direction, for example, you make the transistor faster, and that makes it lower noise. But like many things, that worked for a while until it didn't anymore. And around the kind of 2010s, we really had to figure out what the origin physically of this noise source was. So that's what, with NSF-funded research, I, in collaboration with the Caltech Radio Astronomy Lab, studied. And what we found is that we think this hot electron noise can be attributed to these electrons hopping back and forth between the channel, where they are supposed to live, and then the barrier. And these two films have such different properties that when an electron hops out, it causes a fluctuation in the conductance of the channel, and that shows up as noise. Okay, so how do we make transistors better? Well, this is where KISS comes in. In the field, the focus was really on making transistors faster. And the way you do that is by playing with the composition of the channel, meaning the indium content of the channel. What our research showed is that in addition to that channel composition, we have to think about both of those films, including the barrier, because that's what determines how deep the electrons are stuck in that channel. And so what we predicted is that if we are very careful in changing the composition of the barrier as well, we could actually confine these electrons better and suppress the noise. Now, we've probably all heard of the valley of death for commercialization. I don't know if we were in a valley, but I'd say we were in a shallow depression of death, meaning we had this great idea, we thought, but we needed to get some preliminary data to really show someone we're on the right track. And that's where KISS came in with these technical development funds and allowed us to retire a lot of the risk. So in particular, kind of starting from really nothing, we were able to develop a process to fabricate these HEMTs in-house, actually on the campus. And this is what is now allowing us to then get custom epitaxial wafers with these different compositions, and then fabricate the HEMS and prove out this hypothesis. In addition to that, we now, for all the radio people around here, we have this process, and there's the possibility to make, for the first time, vertically integrated microwave instruments based on the transistors that you see here. This has led to follow-on R&TD funding, which is just about to start. And so we're very excited for the possibilities. So yeah, thank you for listening.
Thank you, Esther. All right, fantastic. Okay, we are going to keep going. Reminder, we've got the Slido up here. We are going to shift gears a little bit. We're going to move away from space to start looking back down on Earth. And with that, I'm delighted to hand over to Dwayne to tell us about a recent study doing just that. So Dwayne, over to you. Thank you.
Thanks for having me. So this study was addressing the following conundrum. NASA's really good, and JPL helping lead that way, of developing new space missions to address science questions for Earth, right? And so you put up a new measurement that looks at atmospheric chemistry, you put up another one that looks at the surface, you pick up another one that puts up ecosystems, and they're all very good. And they tend to last as long or longer than intended. And so you end up getting a community of scientists used to that data and liking that data and wanting more and more of it over time to both study climate or because they're interested in using it for some sort of decision support or application use. And so we get more and more of these instruments up there because we have more and more opportunities to fly new missions and discovery-like missions. But then you get to the point where there's some tension around whether you want to put up a new measurement and continue a past one or just put up a new mission for a new science endeavor. And that ends up resulting in just sort of a tension and a conundrum. And so we asked KISS for help in sort of having a conversation around this. The study co-leads involved Tapio Schneider from here, and his interest in this is because he's interested in developing Earth system models and climate projection models, and long-term observations are critical to that. So he understands the ramification of and the importance of having continuous long-term measurements. And Betsy Weatherhead was a scientist that was really heavily involved in the ozone problem and the ozone recovery, so forth. And again, long-term measurements are really important to that and sustained observations. And so they were the co-chairs. And I regret to say that we didn't have Joe Lazio on our study. We had a very distant second that we were lucky to have. I'm blanking on his first name. Walid Abdullati was on our study, who was a previous chief scientist, and he was the co-chair of our past decadal survey. So he was very interested in the problem. We were super happy to have him. This is a diagram that sort of emphasizes the tension that we were dealing with, or that we have sort of in our country around this Earth system, ecosystem, and enterprise. The top shows sort of what we refer to as a European model, ESA, or European Space Agency. And I'll just point, and then the bottom one is sort of the US model that you can see is sort of divvied up between NASA, NOAA, and USGS in relation to the Landsat program. And that first column is science missions. And NASA conventionally puts up the science missions on behalf of the United States, and ESA has a similar program to put up science missions for Europe. And I'll go clear over on the right side. There's also the one place where we do have continuity, established very well, is in weather, sustaining weather observations for weather forecasting and so forth. So Europe has EUMETSAT, which is largely responsible for that continuity of weather satellites. And in our case, NOAA is responsible for that. And those are really solid programs. About 10 years ago, Europe stood up a program called Copernicus under the European Union, and they have sort of a systematic conversation and program and organization around sustained observations. We don't have the same thing in the US. There's actually, rather than that, there's sort of a tension between NASA and NOAA. NOAA has this sustained program around weather, so they kind of feel like maybe any kind of thing that's sustained might be land in the NOAA bucket. On the other hand, they don't have all that expertise across all the Earth system and those observation developments like NASA does. So in some cases, NASA seems like a fitting place. In some cases, NASA has stood up long-term observations. For example, sea level, there's a record of multiple satellites now. Or GRACE, you might know the GRACE, the gravity mission. There's GRACE and GRACE follow-on and now future continuity. But it's gray for a given area, because it's a gray area in our country of how to deal with that. And the tension, comes down to, if we have a dollar, if NASA has a dollar to spend on a new mission, do they spend it on a new discovery of a new mission, or do they extend the past mission to make sure it's valuable for climate research and other things, or application and decision support? And just to say that we just don't have anything in this country that systematically that helps us with questions like this. Apart from weather, what are our national priorities for sustained observations? There's not just a concerted discussion really on that. What paradigm does the U.S. use for setting those priorities? What organizations or bodies will be chartered to develop those priorities? So anyway, again, we ask KISS for help and just helping us have that conversation, and with the goal of trying infusing it into the next decadal survey or the midterm review and then the decadal survey. And so just with limited amount of time, am I out of time? Yeah? Okay, so I'll just say, we broke this problem down into 3 parts. What to include, and just priorities around that. How to include it from an architecture point of view, both soft and hard, in terms of the observing system or partnerships, and then how to sustain it. And so we ended up having those conversations, embedding it in our study, how to identify priorities, how to develop architecture opportunities, including all the new space considerations, international partnerships, commercial, and so forth, and then considerations about how to sustain it. And that's our study team. A lot of smiling faces there. That was before lunch, which suggests that we were having a lot of fun. And just to say that we wrote a team-oriented paper that appeared in AGU's Earth's Future, and we were infused into the midterm review that just happened about a year ago. They brought up that conversation as sort of a key piece in one part of their outline. And there's also another document that is paramount in this area that's from the President's Office, the National Science and Technology Office, and it deals with a national plan for civil Earth observations, and there's been about 3 of those, and this got infused into the 4th one just recently. So anyway, thank you for your...
Fantastic. Thank you, Dwayne. All right. Super. So just a reminder, please do scan the QR code if you have any questions. I see them coming in, so thank you for that. Next up, we're going to go to biodiversity, and Erica, it's over to you. Thank you.
Great, thank you. I'm Erica Podest. I'm at JPL, and this study was co-led by Kyle McDonald from JPL as well, and City University and City College of New York. He's right here. And Janine Cavender-Barres, at the time, from University of Minnesota and at Harvard University now. So the purpose of this study was, as the name suggests, biodiversity. We have a conundrum too, in the sense that there's a lot of data out there. There's a lot of in situ data, field collections, airborne data, remote sensing data. How do you bring all of this together? Especially in a time when we are in a biodiversity crisis, which has been well recognized and documented. A recent report by the Intergovernmental Science Policy Platform on Biodiversity and Ecosystem Services stated that more species are threatened with global extinction now than ever before. So we're in a 6th mass extinction. And our ability to monitor biodiversity at local scales has led to numerous examples of successful conservation efforts. However, we've not yet been able to adequately create a baseline or monitor biodiversity on a global scale. So that was the focus of our workshop, how to bring together all of these data sets to help get us closer to something that addresses biodiversity at the global scale. And it conceptualized an observational based construct in order to be able to quantify and monitor biodiversity aspects. So our workshop was based on, there were actually 2 workshops, one in 2018, the other one in 2019. There were a total of 39 participants and 25 organizations from 4 different countries. The first workshop focused on what are the data gaps? What are the observational gaps? What are the knowledge gaps? What are the needs? And how do we bring everything together? I mean, the time is right. We've got the data, we've got the technology, the data science, the computational infrastructure. How do we bring all of this together? So the second workshop focused on the implementation on how do we do this. And the recommendation was a global biodiversity monitoring system, a virtual one, where we bring different types of data sets and products. There's space for development and generating products that can address not only science but applications, so end to end. And this workshop has, it's been a little while, so we've got a couple of really nice efforts that it has supported, anywhere from informing mission planning for the SPG mission, including the SPG definition in the Decadal Survey. It served as a motivation for advancing NISAR capabilities for ecosystem structure analysis. So one of the things we notice is the biodiversity work that's being done in the community really lacks from radar observations. We've got a radar satellite that's launching very soon. It's called NISAR, and there's great potential for these observations to address biodiversity related to vegetation structure and structural components of the land surface. Other things that this has helped address has been, or it has supported, was funding a major NSF center, and this was led by Janine. It helped infuse that synergistic value of multi-instrument, multi-sensor measurements for terrestrial ecology. In the early discussions around the 2027 Earth Science Decadal Survey. It was a catalyst for a JPL SRTD effort, and biodiversity effort. Several NASA ROSES proposals were funded because of the ideas that emerged from these workshops. And it led to great collaborations between JPL and other institutes, especially the Smithsonian Tropical Research Institute in Panama. A group of us went there shortly after the workshop, and that started a collaboration around biodiversity in the tropics. And more recently, because of that collaboration there, we carried out an airborne campaign using AVERS-3, which is an imaging spectrometer. And it was based in Panama and Costa Rica, focused on val of tropical vegetation traits for SPG. So, and we have 4 peer-reviewed publications, 1 news article, 1 publication in review at the moment, and it supported also early career scientists. And for one of them, it helped define his PhD thesis and also context for his professional development. Thank you very much.
Fantastic. Thank you, Erica. All right, super. Thank you. Wonderful. All righty. Okay, we are going to keep moving on. Just a reminder, we have the Slido for questions. I see questions coming in, which is super. But without further ado, I want to hand over to Charles for a very timely topic to talk about as well. So thank you.
Saying that I had the great good fortune to work with Paul Wenberg back in 2009-10. We led one of the first, I think it was the 3rd KISS workshop back in the days when KISS was located over in Caltech Tower and before the wonderful facilities that we have today. So I've been an early adopter and had great enthusiastic results working with KISS, so thanks. This is a workshop that we called the Megafire Workshop. It was challenge to use Earth observations. So how might we use remote sensing from space and or aircraft to help understand pre-SIN and post-fire conditions and help manage against these tragedies that are taking place much more frequently. This is an image here showing JPL with the station fire from 2009 in the background. It illustrates really, really, really well the proximity and the dangers of what we call the wildland-urban interface. And so more and more we're seeing large, intense, and highly consequential fires just ravaging this wildland-urban interface. And this was really the motivation for this workshop. This was, again, in the depths of pandemic in 2020 and 2021. We were motivated by the fires that happened, the Thomas Fire that was up the coast here between Ventura and Carpinteria. That was the largest fire in the history of California at that time. In 2018, then, there was the Camp Fire that completely destroyed the town of Paradise, destroying over 19,000 structures and wiping out a whole town there. And so we came together and we were looking at things that might happen. And then, of course, after that, there was the 2021 fire called Marshall, which started on the outskirts of Boulder and burned in towards Denver and took out a large chunk of the Broomfield area there, for those of you who know that geography. And then, of course, what happened around here just this past January. One of the things that I'll say about the Paradise, the Broomfield fire, the Marshall fire, and then these fires here in Los Angeles just this year, is that they all happened outside of the normal fire season. So they all happened in winter, November, December, January. And that's something that we have to deal with as well. One of the key outcomes of this workshop was recognizing the fact that we needed to be more agile in our operations. And so here are sets of images from the space station using the EcoStress thermal infrared sensor that actually show you active fire while it's burning. Down here, Palisades was taken on the 11th of January, and then those images from Eaton were a couple days before that. And so being able to get that information, get it down, and have it in place while the fires are actually ongoing was a major advance. Similarly, Erica just mentioned the Avers 3 sensor. We now have the ability to fly very fast. This is an image from the 11th, but it also flew on the 5th and 6th of January, right as the fires were starting. You can see here over Altadena in the Eaton fire area where everything was burned out. This imagery is also very good at identifying non-natural elements that are left down in the ground, and so we have an idea of some of the challenges that are going on moving ahead. And then for workshop outcomes, this helps secure a $100 million class program at NASA that is called FireSense. In fact, the FireSense team are flying some prescribed burns in the Georgia, Florida area right now. So if you go on the NASA Airborne Science Tracker, you'll see those planes flying. There's a technology program associated with that. There are the technologies that are going on. And one of our leads, George Whitesides, is now a representative from California's 27th District and championing the use of Earth observations and technology from that aspect. So lots of good stuff that's happening and addressing this really, really challenging and important problem. Thank you.
Thank you, Charles. All right, super. So we're going to go to our final update of the day. And with that, I am very happy to hand over to Nick to tell us all about his somewhat recent study on, over to you, Nick. Thank you.
Thanks, Harriet. So I'm Nick Perizou. I'm at JPL. I co-organized this workshop on greenhouse gas and winds back in October last year with Paul Winberg in the back and Mary Whelan at Rutgers University. So the motivating theme for us is greenhouse gas mitigation, net zero carbon emissions. Getting to net zero would put us well on our way to being able to control climate warming. And there's multiple ways to get down to net zero. There's like two things that we can control and one thing that we can't control. And those are kind of the big themes for this topic here. That number one thing we can control is carbon emissions and decarbonizing and getting this red curve down to zero over the next decades using electrification of the grid and changes, more sustainable energy, changes in deforestation, these types of things. Number two is directly removing the CO2 that we emit from the atmosphere using direct air capture or planting of forests or other technologies in the land and ocean. And number three is the thing that we can't control, and these are natural sources and sinks of carbon in the land and oceanic ecosystems. And these represent feedbacks, and we want to be able to monitor all of these things globally, simultaneously. And we're actually already doing a very good job. We have a bunch of instruments in space that are monitoring atmospheric CO2 and methane. We've been doing this since 2002 with AIRS. We have SkiAmaki, we have OCO2, we have multiple NASA, Japanese, European instruments in space. The trick is that it's really, CO2 has very long lifetime, hundreds of years, and it's really hard to trace it back to its origin, especially when you're observing in the mid-troposphere. There's a lot of winds that move that CO2 in the air. And so the challenge for us was to try to combine winds and greenhouse gas measurements to improve the traceability and to better quantify and monitor changes in sources and sinks over time. And so we have 3 scales. We tried to characterize this problem by breaking it down into 3 scales of greenhouse gas and winds. And the first scale we defined as local. This is where you have power plant emissions, very intense point sources, and negative emissions potentially. These are confined to the boundary layer. And the type of emission is also correlated with the type of atmospheric transport, which in this case is turbulence. So being able to observe both the point source plume and the volume of CO2 in the boundary layer through boundary layer measurements can help you better characterize emission rates. The third scale or second scale that you see here is the large region. This is 100 to 500 kilometer scale, the size of a US state. And so this is where you have the predominantly natural sources and sinks occurring from large forested and agricultural ecosystems and urban landscapes. And so in this scale, you see two different types of emissions and transport processes happening. You have the large scale emissions, which I mentioned, and then you have vertical and horizontal transport in the atmosphere by clouds, by horizontal winds, by vertical mixing. And so you have to be able to characterize all of this atmospheric motion together with the trace gases in order to be able to quantify the natural sinks. And then we have this second scale, and this is probably the most important scale that we don't observe currently. The small region, 10 to 100 kilometers. This is where a lot of the human-based emissions and removals occur. And if we want to be able to monitor the effectiveness of these things, we need to be able to observe at this scale. And we also need to be able to characterize vertical mixing. When you're at this scale, you have a lot of exchange between the boundary layer and the troposphere. And you have to be able to monitor both the vertical distribution of that trace gas and the mixing itself to trace it back to the source and sink. And so our workshop, we had, it was amazing. We had a bunch of greenhouse gas and wind experts from all over the world. I had no idea about the breadth of the wind field, and so it was amazing being able to bring everyone together. We learned that there's already a bunch of ways of measuring both greenhouse gases and winds from space. And one of the recommendations that we came up with was we need constellation science. We need to take advantage of the existing observational and modeling tools that we have to better characterize carbon emissions. And we also discussed new pathways forward with technology using LIDAR, hyperspectral sounders to get co-located measurements of both things like water vapor in the atmosphere and greenhouse gas concentrations, and a number of other pathways that could get us improved ability to attribute carbon emissions. And I'll just leave it at that. Thank you.
All right, fantastic. I can't believe we got through 16 updates from KISS studies. This has been amazing. All right, so we've got a couple more minutes before we're going to head over to our networking reception. And before that, I just want to say a few words. Firstly, thank you so much, everyone, for being here, for your interest in the range of studies that we've been supporting over the last few years. I hope this has given you a little bit of a flavor of the kind of topics that we are here to support here at KISS. So I'll start that by looking backwards a little bit. Just a reminder, if you've been involved in any KISS studies and this has inspired you or reminded you of the fantastic outputs that maybe we haven't been able to share here today, we do want to hear from you. So please do either reach out to me directly, come find me at the networking mixer, or you can fill in this quick form as well. That really helps us to celebrate, showcase, and champion the outputs that are coming out of the activities that we are supporting here as well. The other thing that I really want to acknowledge is that we have been hearing here today about some of the amazing outputs and follow-on activities that have happened of recent studies, but also studies that have happened in the past years as well. And this would not happen without the past leadership of KISS. So I would just like if Tom Prince wouldn't mind just standing up and just waving to everyone here. So Here at KISS, we are undoubtedly standing on the shoulders of giants, and I just want to explicitly thank both Tom and Michelle for their outstanding leadership of KISS over the many years that they've been involved creating, driving, and championing this institute as it has gone forward. Michelle unfortunately couldn't be here today, but Tom, I'm so glad you could be here, so thank you so much. So if I can ask everyone to please personally thank Tom for everything that he has done at the Mixer. We have a little gift that unfortunately is stuck in the US Postal Service. But we will make sure that it finds its way to you. And I just want to say, on behalf of the KISS community, again, a huge thank you to Tom and Michelle for everything that they've done to build KISS to what it is and allow us to be able to celebrate everything that is being done here. So again, another round of applause and thank you to Tom. So if this event has inspired you to get involved in KISS activities in the future, if you have a topic in mind that you would like to bring together, convene a community, help develop those revolutionary ideas of the future, maybe there's something you haven't heard about today, but you're dying to get started and build that community to take those ideas forward. Just a reminder, we do have an annual call for KISS studies. That is taking place in the fall, so please do stay tuned. Around the beginning of October, we typically open up our call for KISS studies. That goes in 2 rounds, so we have a first stage where we're looking for a 1-page concept to help generate those ideas. You get feedback from our steering committee to help refine those study programs and proposals by the end of the year. And then we make our selection at the end of January each year as well. So please do reach out to me if you've got any questions about our proposal process and how we can support you going forward. But also we really encourage you to start those conversations now, right? Anyone who's been involved in a KISS study before can tell you, or anyone who's been part of leading a KISS study can tell you that it's a lot of work, but you get out what you put in. So I encourage you to start those conversations, make those connections, and hopefully do that over our networking reception as well. So speaking of that, some people have been particularly proactive and had reached out in advance and that have identified some topics that they're particularly interested in talking about today at the Mixer. So I'm just going to run through these, and if you hear me saying your name, please do stand up and give a little bit of a wave. And if you're interested in talking to someone about that topic, please do make that connection at the networking Mixer. So James Keane is here to talk about next generation planetary geodesy at Mars, Enceladus, and beyond. So please do talk to James if you're interested in that. Hiro is one of our rockstar study leads for our 2025 program. So if you want to talk about boldly going where no robot has gone before with radically adaptive space systems, please do speak to Hiro. We have Kyle McDonald here, who is interested in talking about characterization of structural diversity in forests using portable scanning LiDAR. So Kyle, hand up. Yes, please do talk to Kyle. We have Seth Park, who's interested in astrovirology, which is very interesting. Yes, so please do talk to Seth if you're interested in the promise and challenge of hunting for the smallest life. Jonathan Soda, who is interested in exploring how AI can be used to digitally prototype spacecraft design and applying generative AI to spacecraft mission and early stage development. So, Jonathan, if you are here, yes, in the back, please do talk to Jonathan. Chris Yanker is interested in transformational exploration with advanced computing. I don't see a hand raising, but we've got a few like AI, machine learning kind of topics that are of interest to folks here as well, including Sejong Kim, deep learning models for predicting experimental results. I don't see a hand raised, but that's okay. We have Hans Kraus, who's interested in quantum sensing for magnetometry. I can't even say that word. So please do talk to Hans, because he's much better at yeah, there we go at the front. Thank you, Hans. Much better explaining that than I will be. And then we have Christian Stone, who's interested in modular 3D printed, or another tricky word, based thermal isolators. Please do talk to Christian. Is Christian here? Yes, all right. And Christian can tell you how to pronounce that wonderful word as well. I hope this is just the start of some of those fantastic conversations and many other things before that as well. Before we head off to the networking drinks, I just wanted to hand over to our fantastic director, Bethany Ellman, to say a few words as well. So Bethany, over to you.
All right, so thank you, Harriet. And this is, a new format for us where we're both trying to showcase the past, present, and future of what is going on at KISS now, and then use that as a seed for you to mingle. So we previously, just had mingling in the courtyard, but now you're seated with all of these ideas, both from the presentations, those who want to speak. I do want to emphasize that if you have an idea that you think you want to have a KISS workshop, talk to me and Harriet. We can help be matchmakers for that. Also, could I have members of the steering committee just put their hands up again? All right, we've got a number. Take a look around, keep the hands up. We've got a number of members of our steering committee who you should also seek out for advice for your ideas. We are here to get the best ideas into those workshops. So as we draw to a conclusion, first of all, I want to thank Harriet and Antonio and Janet, who's left, and then our KISS affiliates, for all of the work, Annika and Kevin, for running this event. All right, so huge thanks here. And I'll reiterate the thanks to Tom and Michelle, and really to all of you for creating this KISS community, because the reason that these ideas get legs to them is the creativity of this community, and then it's the hard work put in to build those relationships, to take those ideas forward. So keep bringing the good ones. Let's foster those at the reception tonight. And I will turn it back for any final logistics to Harriet. Thank you.
Thank you, Bethany. All right, so the final logistics are super simple. We are going to make our way over to the Keck Center courtyard, which is just across here. If you don't know where you're going, follow one of those people that raised their hand at the beginning who's been to a KISS workshop, literally just across there. We've got drinks, we've got refreshments. Please do make the most of that, continue these conversations. And again, thank you so much, everyone, for joining us. It's been a real pleasure. Thank you.